We want to find the linear approximation to f of x comma y at the point 2 comma 4 comma 10, then use a linear approximation to approximate a new function value. Notice how this function value is near the given point. So the linear approximation to a function of two variables is L of x comma y given here, where it's going to be approximately equal to f of x comma y as long as x comma y is near the point where we find the linear approximation, which is the point a comma b. So let's take a look at this graphically. Just like in 2 dimensions, we can use a tangent line to approximate a function value. In 3 dimensions, we can use a tangent plane. So here we have the surface graphed in purple. The given point is this red point, and the yellow plane is the tangent plane. So when making a linear approximation for a function of two variables, we're actually using this tangent plane to approximate the new function value. So going back to our notes, in our case, our linear approximation, L of x comma y, at the point 2 comma 4 would be equal to f of a comma b. In our case, notice a comma b would be 2 comma 4, and x comma y would be the new coordinates 2.17 and 4.29. So f of a comma b would be f of 2 comma 4 plus the partial with respect to x evaluated at 2 comma 4 times x minus a, that'd be times the quantity x minus 2, plus the partial with respect to y evaluated at 2 comma 4 times the quantity y minus b, or y minus 4. Now if we look at this equation more carefully, notice how this is just the function value at the point of tangency, and then plus the sum of these products is just differential z. So all of this is differential z, the change of z along the tangent plane, which we're using to approximate the true delta z, the change of z using the true function. Because remember, differential z is defined here, and if we compare this to our linear approximation, notice how differential x is just x minus a, and differential y is just y minus b. So our next step will be to find our partial derivatives and then evaluate them at the point 2 comma 4. Let's first rewrite the given function. We have f of x comma y equals, notice how we have a square root 2 in the denominator. Let's write this as 5 divided by 2 to the 1/2, and then we'd have times xy to the 1/2. In this form, it'll be easier to find our partial derivatives. So the partial with respect to x will treat y as a constant and differentiate with respect to x. So notice how we would multiply by 1/2. So let's write that as 5 over 2 times 2 to the 1/2. And then we'd subtract 1 from the exponent, so xy to the negative 1/2 times the derivative of xy with respect to x, that would be y. So simplifying, let's write 5y in the numerator, and then for the denominator, we have this 2. We'd move this down to the denominator to make xy to the 1/2. We already have a 2 to the 1/2 there, which would be equivalent to the square root of 2xy. Now we want to evaluate this at the point 2 comma 4. So we'd have 5 times 4 divided by 2, and then we'd have the square root of 2 times 2 times 4. That's the square root of 16. So this simplifies to what? 20 over 8 28ths. Common factor of 4. This simplifies to 5/2. And now we want to find the partial with respect to y, treating x as a constant and differentiating with respect to y. So again, we'd multiply by 1/2, so we have 5 over 2 times 2 to the 1/2. Subtract 1 from the exponent, xy to the negative 1/2, times the derivative of xy with respect to y, which would now be x. So now we have 5x divided by 2 times the square root of 2xy. Again, evaluating at the point 2 comma 4. Now we'd have 5 times 2 divided by 2 times the square root of 16. So now we have 10/8, which simplifies to 5/4. So now we have all the information we need in order to find the equation of our linear approximation. We have this value and this value. So now we'll perform those substitutions and simplify to find our linear approximation at the given point. We would have L of x comma y, again at 2 comma 4, would be f of 2 comma 4. Well, the function value here would be the z-coordinate of 10 plus the partial with respect to x at 2 comma 4, that's 5/2, times the quantity x minus 2, and then plus 5/4 times the quantity y minus 4. We will go ahead and simplify this, but notice how for the second part, to find a linear approximation, we would just simply substitute the new x and y values into L of x comma y. To simplify, we'll distribute, so we have 10 plus 5/2 x minus 5 plus 5/4 y minus 5. Notice how we have 10 minus 5 minus 5, that would be 0. So our linear approximation of f of x comma y at the given point is L of x comma y equals 5/2 x plus 5/4 y. And now to use this linear approximation to approximate our new function value, we just need to find L of 2.17 comma 4.29. So we'd have 5/2 times 2.17 plus 5/4 times 4.29. Let's go to the calculator. We have 5/2 times 2.17 plus 5/4 times 4.29, which gives us 10.7875 for our approximation. So again, the idea here was that f of 2.17 comma 4.29 is approximately equal to L of 2.17 comma 4.29, which is 10.7875. So we found the linear approximation to our function f of x comma y at the given point here, and then we use this to approximate a new function value, which we found to be 10.7875. I hope you found this helpful.